Hi, everyone, and welcome to PyData Global. We're excited to have you join us. Please feel free to use the chat to connect with fellow attendees and share your thoughts during this session. If you have any question, please feel free to post them in the Q&A tab, and we'll address them at the end of the session. I have the wonderful honor of welcoming Art Anderson, who is the Director of Developer Advocacy. So please help me provide a warm welcome to Art. And Art, the stage is all yours.
Awesome, thank you. Hi, so welcome everybody. Thanks for the intro, Patricia. So my name is Art Anderson, Director of Developer Advocacy at Aerospike. If you're not familiar with Aerospike, we're a NoSQL distributed database, and we'll be talking a little bit about the usage of Aerospike in building out this hybrid search today. But the focus is really on the kind of journey of going through and exploring combining vector search and a keyword search together using Python to then create a better site search for aerospike.com. So there's a lot to kind of cover, and I'll try and keep an eye on chat and things like that, but hopefully we'll have a little bit of time at the end for questions if anybody has them. We're going to talk a little bit about just like the overall structure as we go through this. So just, why are we building a better search, and how did we kind of go through the different pieces of that? So looking at our semantic search or working with vectors, getting into our keyword search, so looking at like inverted indexes and some different ranking algorithms, and then tying everything together as far as the ranking and sorting of the two items, the keyword and the vector go, and then putting it all together in a front end and so on. So with that, let's get started and talk about kind of why we built a search, right? So aerospike.com, our initial search was, it wasn't terrible, but it wasn't great. It was effectively broken. Filtering was not really working well. Content was hard to find. It didn't surface things in an appropriate way. We were using just a third-party search appliance that, they did their own scraping, and we didn't have a lot of control over. So we're launching a new vector database actually next week. And so as we were kind of going through and beta testing things, we thought, why don't we just eat a little of our own dog food, and let's use Aerospike to build search for our site. So this is going to help us to kind of open the door for more complex search functionality for users to be able to surface more content in a more kind of relevant way, and also just kind of a fun project, right? So this is something that I worked on with two interns that are probably more of the brains behind this than myself, but they came up with some very clever ideas and figured out ways to tie all of these things together. So we're going to highlight a lot of their amazing work here today. So the overall plan that we were kind of laying out here as far as how we build this out is, we're going to look at the data, so aerospike.com. So this is basically all of our kind of web properties. So we have a marketing website, we have documentation within that, we have developer kind of content, so code samples, things along those lines, API docs. We have a support knowledge base as well that we wanted to kind of capture within all of that. So we went out and tried to figure out a way to be able to capture all of that stuff. It's all public data, and even though some of these items live inside of repositories that we have access to, it was actually easier for us to scrape the data in kind of like a standardized way to be able to pull everything into the database, and we'll talk about that in a little bit as well. So we're using Scrapey as our scraper, and then for our keyword index and for our vector index, we're doing some data prep utilizing Llama Index and Spacey. We're using Uvicorn and Fast API to serve these things up. And then all of this goes into the Aerospike database. So key value and vector kind of living together. We're going to talk a little bit about Gemini, so using that to create embeddings or the vectors for our vector search, and then tying it all together with like an Astro React based front end. So, like I said, the data. Main website, our documentation, our developer hub, all of that. So Scrapey was the kind of like the easiest tool to work with as we were getting started. So it's something I was familiar with, and my interns, Tori and Vibov, had also kind of played around with. So it was a kind of just an easy choice to start messing with that. I had built a kind of like a RAG application prior that was playing around with some of the Aerospike documentation already. So we had a lot of the bones, and then just we're able to create some kind of like standardized XPath queries that allows it to target very specific information on every page. And so when Scrapey grabs the data, we're actually converting that data into Markdown. And then that Markdown is what's going to go into Llama Index for like chunking and then embedding or the spacey kind of filtering. So for vectors, like I said, we use Llama Index. This is super easy to use. It's lightweight, and it's just a very comprehensive tool chest of different kind of ways to interact with unstructured data. So when we're working with larger documents, we want to break these things down into smaller chunks. So one, they're easily handled better, but also as we move forward, we may want to start interacting with an LLM in like a RAG application. So we'd be able to pass along these smaller chunks to that RAG. That would then allow us to stream back a response from an LLM for kind of more domain-specific information about answering questions if we wanted to do that. So we're breaking every document down into about 512 token chunks from Llama Index with about a 32 token overlap. So that allows us to hopefully carry context from one chunk to the next, and not lose kind of the overall context of the document in smaller chunks. So we go through and like I said, we prep those and then send those in for embedding or generating vectors that we then store in Aerospike's vector database. So if you're not familiar with vectors, vectors are just, it's literally like a list of floating point numbers. Now, it gets far more complex than that, but not anything that we need to go into in this session here. But effectively what we're doing is we're capturing semantic value or semantic meaning of our unstructured data in a like consistent and easily measured kind of object. So it takes this like high volume data, reduces it down according to meaning. It's kind of like the lossy algorithm for JPEG compression, right? So you're not going to be able to take a vector and then like get the data back from that, but that vector has kind of captured some meaning within it from the data that we're embedding. So we used Gemini. So this is Google's Gemini model. I'm sure you've heard of it by now. We actually started out using Nomic AI, but we found that hosting that ourselves was a little bit slow. Not that it wasn't a great embedding model. It was. I mean, I would highly recommend Nomic AI for anybody that wants to kind of play around with this. It's a very, very good model. But Gemini is fast, and we had like Google credits. So it was a pretty easy choice to say, all right, well, let's use this API instead, and we'll just kind of pay as we go at very, very low cost. So Gemini creates vectors of 768 dimensions. And like I said, it's fast, it's easy, and we get these back really quickly. And then we're actually, as we generate vectors on content, right? So anything we're scraping, that's getting stored into our database. But as we'll see, as we get into kind of like the flow of a search, we're also going to be generating vectors on queries. And so using Gemini for that as well, you're always going to use the same model for the query versus the content. But we're then actually using a LRU cache, or like a least recently used cache, to cache those vectors of our queries, so more common queries can get faster results because we won't need to re-embed that if we already have that vector. So we're storing the data in Aerospike. Like I said, Aerospike is a key value store, well, I said earlier, we're a distributed NoSQL database. And so at our core, we are a key value store. And so Aerospike is really just like the storage backing for the vector search, and then also, as we'll see, our keyword index. And so the way Aerospike vector search works is there's actually a service running alongside of the database that is implementing a hierarchical navigable small world search algorithm. So if you're not familiar with vector search, I'm not going to go too in depth on this here, but basically what we're looking for is approximate nearest neighbors for our vectors. And so through this, we're doing a cosine similarity. So create a vector on our query, and we're going to create a vector on the content, and then we're going to just basically measure the angle between vectors to find who's the closest, right? So where are the nearest neighbors within the database. And so Aerospike has implemented a kind of distributed HNS-W that works really well, scales nicely, it's very fast. And then, of course, Aerospike's the key value storage backing is also incredibly fast. So we get really good results when we're looking at the kind of vector side of the search. So lots of speed. And now we're not working with like a ton of data here. It's probably about 6,000 records or vectors overall that we're searching over. So that's a fairly small data set in the world of Aerospike, but yeah, it does an amazing job. So just there's my like Aerospike plug for the talk. So querying the data, like I said, a user is going to come in and they're going to ask a question, or potentially even just like do a keyword search. We're still going to utilize the vector search for part of that. And so that query is going to go into our Gemini embedding model, or potentially pull from the cache if somebody's already asked that question, that vector's been created. Now, we're just a note on that cache. So we're not actually doing like, we could be doing like semantic caching. So like, is this question semantically similar to another question that somebody's already asked, and then using those vectors? We're doing just straight up, is this the exact same search? So we could optimize later on down the road, but for the moment, there's not really like a need for that. We're already kind of seeing pretty great results as far as like speed and all that goes. So it's an optimization maybe later on down the road, but for now we're just doing an actual like, just is this the exact same query that somebody else asked? And then if we match that, we'll grab those vectors instead. But so we get that vector embedded back, and then we perform the search across Aerospike. Aerospike then returns back to us the top end results. So depending on like the search that we're going to do, generally we're going to return like maybe the top 100 results from Aerospike. I mean, these are going to come ranked and ready to go. So there's not really much manipulation that we need to do on the vector side to then identify kind of the ranking of the best fit to the least fit. So on the keyword search, this is kind of a different approach here. So we start at the same place with the scraping and even the chunking, right? So we're doing all of the kind of keyword processing on the same chunks that we're doing our vector embeddings on. And so if you're not familiar with inverted index, this is actually a super common search engine data model. It's effectively where we're going to search keywords for documents instead of parsing through lots of documents to find keywords. So the way that this is set up with an Aerospike is we have every keyword that we come across when we're processing the data becomes a record in Aerospike. And that record is going to maintain a map And every key in that map is going to be the document chunk that contains that keyword. And then within that, the value for that document chunk, we're maintaining some kind of like metadata, if you will, about like the position that the keyword shows up in, the frequency that that keyword shows up in, and then we're even implementing some kind of like proximity so that we can see later on as we process the data that we return from the keyword search. If you have multiple keywords, like is there proximity between those two keywords within a single document? So we're able to kind of get a pretty good idea of not only what documents have these keywords, but also which documents have these keywords showing up more frequently than others, and then potentially even the proximity between multiple keywords within a search. So for this, we're utilizing Spacey. So Spacey is a great natural language processing library. We're using this for tokenization, stop word removal, and then lematization. So kind of like getting to the root word of individual keywords. So each of these chunks goes through Spacey, and then we use the kind of resulting tokens, which would be all of the keywords within a specific document, as the kind of building block for that inverted index. So like I said, this is also being stored in Aerospike. So Aerospike is super fast, and it works really well with complex data types. So like I said, each of these keyword records is a map. And so being able to traverse that map and find things, or like when we're cleaning up an index, maybe a document's been removed or something like that, it's really easy for us to be able to kind of access those very specific areas of the index individually. Now, with the Spacey stuff, or with our keyword index, right, very similar. You're going to have a user query. It goes through that same Spacey filtering for the tokenization, lematization, stop word removal, and we get our kind of root keywords within the query. We then use those to pull up the records within Aerospike that then give us the list of all of the documents that have those. But that is not coming back in any specific order. So when we get those results, we need to actually do something to those to identify whether or not, or really what the ranking of the best results or most relevant results within that keyword search are. And so that's where we turn to this BM25, or best match 25. So there's a whole lot of stuff going on here. But effectively what this is doing is just looking at each of our documents, the query terms, and then we're actually pulling like our inverse document frequency. So like effectively, like how often is this keyword showing up in this document versus all documents. And then we're applying some additional kind of control for, how does this apply across the overall average document, and so on. There's a lot going on here, and we definitely don't have time to dive in too deep. But this is basically best match 25, or BM25, is kind of applying this the term frequency and inverse document frequency, along with some additional controls to give us some pretty darn good results as far as ranking what comes back within our keyword search. Now, we have two searches. These are running in parallel as a user query. So while we're doing our vector search and embedding and comparing vector angles, we're also doing all that keyword searching, and we need to put the two together because we're going to see some overlap in there. At least we hope to. And then we're going to need to identify, like, did something come up more frequently in our keyword search versus our vector search? And not to mention too, with this result, we're looking at document chunks, right? And so we need to also identify, how many chunks of a specific document maybe showed up, and how do we weight documents that maybe have more chunks than others. And so maybe like one document is a very short one, so when it shows up, 100% of the chunks have, and another document is incredibly long, and when it shows up, 95% of those have showed up, right? We need to be able to kind of give a weight to the fact that, well, this one's really short and this one's really long, and so we have to put these things together. And we tried a couple of different ways to do this. We started with semantic re-ranking, thinking, okay, well, this would probably be an easy way to do this. We'll just kind of like have it re-rank everything and then like just combine all of the documents together. So we tried two things. We used Gemini because we're already using that for our embeddings. Um, Pros to this, it was fast and cheap because, again, Google credits. But the cons, it was bad, like really bad results. We would get our keyword ranking results, we would get our vector results, we would look at those individually and be like, this looks awesome. And then we would put them together with the Gemini semantic re-ranking, and it was terrible. I'd be like, wow, that like totally flipped everything around into a way that just does not make sense. And like, we understand the results that we should be getting back, right? Because we work with Aerospike, we understand the documents and things that are out there. It was bad. Cohere, on the other hand, gave us really, really good results, but it was slow. I mean, it was adding about a half a second to every search, and it cost money. Like we had to pay, and so we didn't really find semantic re-ranking to work well for us. Not that this won't work well for other applications, but just specifically for ours, it didn't seem like the right choice. So we switched to math, right? So reciprocal rank fusion is a fairly simple implementation where we're just looking at every document across all of our different retrievers, and then just looking at the ranks within those and building an overall ranking system that we can then utilize to combine these things together. And we've found that one, this is incredibly fast, and two, we get really, really good results from that. So that was like kind of the big kind of changing or kind of different point for us when we were able to really kind of uh, see a huge optimization speed, and then also on top of that get amazing results back. So we're really happy with reciprocal rank fusion. Now, to tie all the things together here, our server and API, pretty straightforward. So fully built in Python using fast API and Unicorn. We're using gUnicorn as our kind of like production deployment. I love fast API. It is super easy to work with, really great performance. And so just, hands down, probably like when I'm doing anything in the world of Python, this is where I'm going first for that, or at least web app wise. The front end, well, we're really combining this into the existing aerospike.com website. So built using Astro, which is like a kind of a framework for removing JavaScript where you don't need it, but being able to integrate with React and a bunch of other kind of like JavaScript or React based frameworks. So this is kind of like a two-stage search. We have like an initial modal pop-up where you can search anywhere in the site and you get like top 5 matches. The goal here is that those top 5 matches are going to be the best matches for you, and you won't actually have to go to the actual search page. But you can then go to the full search page and then see all results and paginate through them if you want to be able to look at more stuff. And so this is fairly simple, just like a call to our fast API endpoint, and then we're just showing this data back over on the Aerospike website. So where do we go from here? Looking forward to the future, right? I had ChatGPT create this image for me, and it told me this is the perfect world where improved search has transformed daily life and so on and so forth. But yeah, we're probably just gonna build a RAG, and then we'll start to implement more complex kind of like search, and optimizing it for optimization's sake. Not that we need to, but just because we're learning and we're playing around with it, and it's a lot of fun to be able to utilize Aerospike in a real world scenario that then users of aerospike.com can kind of interact with it and know that they're using the product behind the scenes there. So awesome. If you're interested, you can try our Aerospike vector database for free. We have a QR code here on the right-hand side, and like I said, this is going to be kind of like released for general availability on, I believe, the 12th is what we're shooting for. But this will let you spin up a little sandbox environment, and you can play with it right now. And then if you want to join our Aerospike Discord community, please join, and you can come out there and ask questions as well, and get to know Aerospike. And we'll be, I still have a little cleanup to do, but we will be open sourcing all of our code that we're using for the search engine as well. So you'll be able to, Discord would be the best spot to get the update for that when we do have that code available for folks to go and start messing around with this on their own. So I'm going to switch back over here and see if we can answer some questions. Yeah, so I see in the Q&A, we'll be able to get a copy of the slides. Yeah, I will make sure that I'll have them up on our Discord community, but I will also make sure to, I think I can add these to the PyData Global schedule. So if you look at the schedule, I'll be able to, I'll throw those up there, but I see Peyton nodding yes, that it seems to be the right way to do it. So
Yes,
we'll do
we
that
also
there.
the feature on the right-hand side, the little paper with the clip on it, that one you can add resources to if you wanted to just go ahead and add it directly to this presentation as
Oh,
well.
nice. Okay. Yeah, I think I have to make a PDF first, but I will make sure to get that out to folks. And then yeah, just in the chat. Oh, thank you very much. I'm glad you enjoyed the presentation. And so yeah, I know we have just like 2 minutes left here, but I appreciate everybody coming and checking this out. And yeah, I hope you're having a great time thus far, and enjoy the rest of PyData Global.
Yes, big thank you again, Art, for this presentation. Like you mentioned, if you want to continue the conversation, you can use not only the Aerospike Discord, but we have the PyData Discord as well, where you can ask some questions, and also the lounge feature through AirMeet. But again, thank you so much for your time today, and I hope you all are able to attend some other sessions and continue enjoying the conference. Thank you.
Thanks.